It's a good opportunity to talk about the supercritical pipes here, not for any other reason, because most of the people who have talked about these ideas are present in this room. So, if I make this, I cannot change screen. This means so what we mean by supercritical pirates, especially in high-end astrophysics, everybody of course knows about nuclear pirates, atomic bombs, etc. But in relativistic outflows and in high-end astrophysics, this is much more obscure subject. And basically, as I understand it, it includes, it's a nonlinear process that basically changes the energy that is in one thing, that species, for example, in protons, into something else explosively. These ideas have been flown for quite some time. For example, Boris and Svensson had this idea about the proton-duty cycles back in 16 years ago. Then John Kirk and I, we talked about the Perl synchrotron synchrotron loop. And now recently, our organizers are talking about photon breeding, and Vinus Kazans and I talk about supercritical GRBs. The ideas are the same, basically that you have energy in protons and somehow you convert it into something else. And of course there are other related nonlinearities in the supercritical pipes, and we will hear about this from Teresa and Lucas. In high-energy astrophysics, most people are not, especially in radiation, are not familiar with nonlinearities, because what in a nonlinearity you can introduce, for example, into synchrotron radiation. You put so many electrons in the source, and if they radiate, you take so much luminosity out. But the point is that, for example, as in Compton catastrophe, that we have these ideas in AGNs, for example, if you take a network of things, then you can have some things that you don't expect. So, for example, assume that you inject in a sphere some relativistic particles with a luminosity. In other words, you give a rate of energy in here, and if you have cooling mechanism, for example, magnetic fields, soft photons around or whatever, then the particle radiate their energy. In steady state, for example, you have, or if this is constant, what you produce is basically what you put. So, for example, if you have electrons and you make them radiate, then you have a photon luminosity here that I take it, for example, to be constant, and at the same time the particle energy content of the source is low because your energy that you put in your particles is burned from the radiation mechanisms. On the other hand, if you have cooling mechanisms which are not efficient, then the particles cannot radiate their energy, so they start accumulating inside the source, and therefore the photoluminosity can be very low, but at the same time the particle energy content can increase in time. So, as the energy increases, the particles become, in some cases, supercritical. In other words, they can reach certain conditions that they can convert all the accumulated energy into radiation or into something else, and therefore, all the energy that is stored can be changed into a photon burst, for example, which is basically has the same energy as the luminosity over time that you saw in the previous steady state. And at the same time, the particle energy cannot grow anymore, and because of the photons that are produced spontaneously in the system, they can cool and they can go back into a low subcritical state. So, back many years ago, with Kirk, we tried to think of a loop that can produce such a situation. And one can take two things. One, assume that you have protons in a source. Then there are two things that protons can suffer energy energy loss from. One is photon pair production, and the other is photopion. And then for electrons, there are two basic ways they can radiate and lose energy. One is electron synchrotron radiation, or can be inverse Compton-Stein. For reasons that will become clear later, we decided to stick into these two, and we thought of the following loop. Assume that you have a proton, which is relativistic, which interacts with a photon. If this collision is over the threshold for pair production, pair hydrogen production, then you produce an electron-positron pair out of this photon. And now these photons can radiate synchrotron radiation, which most people think that, okay, it escapes the system, all right. But what happens if these photons, at least one or two of them, of the many synchrotron photons that you radiate, do not escape but go back and meet other protons inside the source and make more electron-positron pairs. In this way, you can exponentiate your photon growth, and then you become supercritical. Now, as any supercriticality, you need two criteria. It must be sufficient and enough. It must be, one thing must be the feedback criterion in order to have this process, and this concerns the energy of the individual protons that you must have in your source in order to start this loop. The other criterion is the matrix stability. In other words, you require enough protons in your source, so the photons that you're going to create are going to produce before they escape. So these things must be simultaneously fulfilled in order to have this supercriticality.
I mean, that in order for that to happen, it requires Thomson gaps to be used, no?
No, but we come to that. For the time being, I idealize the whole thing. I assume I have a proton source, say relativistic protons of a certain energy, monoenergetic, all right? And assume that for some reason electrons and photons are very low in the source. So I'm trying to work the basic principles. When we come to practical reasons, I will answer your question. But now I want to make it as idealistic as possible, as clear as possible. So that's why I consider only these things. So for the feedback criterion, assume that the following thing, that the electron Lorentz factor that is of the Lorentz factor of the electron positrons which are produced have the same Lorentz factor as the protons. This is, in other words, you assume a delta function relation. And also assume that the emission of the photons, which are these electrons are produced, are all radiated at the critical synchrotron frequency. They are monochromatic, in other words. So it goes like magnetic field times gamma squared, and if you normalize this to MC squared, then you can use the small p, which is the magnetic field over b critical.
Oh, excuse me, point one. Which pairs are produced with the Lorentz factor of protons? Which process?
You have a photon, and you have a proton, so you have gamma p goes gamma
This is
electron positive.
Poutanen.
Oh, sorry?
I guess this is not.
Sorry,
Far from correct.
P is
Yeah.
P electron positive.
Yeah,
But simpler.
I see. I guess the pair in reference system is much.
But you don't care about the rest frame. You're interested in your frame. So in my sphere, I have protons which have energy of gamma mp c squared.
The correct thing is that the Lorentz factor of pair is of the same order as the Lorentz, as the energy of the photon in the proton rest frame.
Yes,
But
then,
not.
But then I'll show you later.
You have to conserve momentum.
No, this is, if you look at the papers working on better hydrogen production, in a relativistic case where you have soft photons producing pairs on relativistic protons, you see that this is not very bad assumption. In other words, the electron positrons are produced, basically they take then they have a small inelasticity. In other words, you say that the energy loss is ME over MP. This is what you imply.
I still doubt. This is correct for pion production.
No, for pion production, it's more.
It's not for correct.
No,
for
no, no.
production,
It's not for pion. For pions, you produce the elasticity much higher than
The
this
issue
process.
is that in this process, the momentum transfer, the transferred momentum is pretty small.
Yes, but
Yeah.
still, when you make the
In fine production is large, and therefore it's correct.
the inelastic, well, the inelastic, it's well known that the inelasticity in Bethe Heitler, kappa, in other words, how much energy the proton loses is of the order of ME over MP, while for photopion, this can be of order of 20%.
Ah, yeah,
It's much,
yeah.
much higher.
Okay, agree. Yeah.
All right? So
Yeah,
it is-
agree. Yeah, agree. I just,
But on the other hand,
yeah, I just sorry. I just mixed Lorentz factor with energy. Yeah.
yeah, no. on the other
Yeah, that's right. Yeah.
Put the lights on that.
On the other hand,
Yeah, that's my point,
this process has a much higher cross-section than photopion. Okay, so it has smaller elasticity, but much higher cross-section. So, if you couple these two things, you find that in order to have synchrotron photons that are energetic enough to produce on the protons, you need gamma p to be greater than 2 over p to the 1/3. So for b equals 1,000 Gauss, gamma p is of order of 3,000. So it's not that extreme number. Now for the marginal stability, one has to do some stability analysis. So one can write down two kinetic equations, one for electrons and one for photons, and assume initially that electrons and photons are at a very low level, and you are looking for growing solutions in this system. You assume that your protons have a certain distribution, and this is what I told you earlier, that you fill your volume with protons, you assume that you have some energy, then some power law or whatever. And therefore, you couple, these are the synchrotron term, this is the synchrotron loss term, and this is the synchrotron emissivity term that goes into the photon equation. And here, as injection for electrons, you have the Bethe Heitler production. And now you can make a stability analysis of this system. And you find in simple words the following, that you need basically the optical depth of photons on protons to be greater than 1. So if you have a power law or with, in protons with some normalization NP0 and the power law index of minus beta, you find something like this. This is the cross-section for photopion, for photopion production. And this is basically a plot showing what happens. You find that below this full line, you are in the stable regime. This is M0. In other words, this which I use as a free parameter. For low gammas, no matter how many protons you put there, you never meet the feedback criterion, so therefore you can have as many protons as you want. You never become supercritical because simply you don't satisfy the feedback criterion. On the other hand, if you have protons of higher energy, then it's possible to have regions where you become unstable. Now the question is that once you become unstable, then very quickly, once you move inside the unstable regime, the photons start growing like e to the st. S is the mode here, and for s equals to 1, 0, you're in the marginal stability. Or in the stable regime, of course, you are negative. In other words, photons go away. You cannot sustain the photon center system. But for s equals 1, that comes a little bit above the s equals 0 energy, density, you start becoming very unstable. In other words, the photons grow very much on light source light travel times.
I'm still confused. Can you remind us what is the
Sorry?
sigma peak. What is the cross section for this process roughly?
For this process can become about
10 minus 20.
it starts
minus
of
20.
course at 0 at 2 mc squared at threshold, and then it becomes about a tenth of the Thomson cross section. So
your
goes logarithmically.
Thomson dash is
This point.
more than 10, right?
Yeah.
So what you're relying on the Klein-Shina effect to...
But here I don't have any inverse complex scattering to worry about the Klein-Shina effects. It's simply because the photons are not that energetic. The photons that are producing this whole thing are not energetic enough, because I assume that this is the energy of the photon. It's not particles at rest in the relativistic photons. It's relativistic particles, and therefore you require photons which are not of very high energy. In other words, for this example, I think I need something like few eV photons to start the whole thing, because the protons are relativistic. Therefore, they meet the threshold requirement when they collide with photons. So it is not something that I have protons at rest and I need much higher energy in photons to produce this. I have relativistic protons and I need low energy, relatively speaking, lower energy photons to start producing all this.
But then you need to boost the energy of the synchrotron photons in order for them to be able to pair produce, right?
No, you don't need to boost it. Why you need to boost it?
No,
Because
it's the rest of the photon. The proton has the proton energy, but
In what frame?
but
Right, once
When you transfer...
But I work
once
always.
you pair produce in
I always work in minus frame. Okay, so all these relations are very well. We know the rates and everything in our rest frame. I don't have to go back and forth to frames and everything. Okay, I hope it is.
So 10 to 6 is in the rest frame.
Yes.
The common frame is like 10 to 10
not the proton rest
to
frame.
3.
My frame.
But not in the shock frame. And
I haven't talked about shocks.
So how do the secondary photons have enough energy in the proton rest frame to pair produce a second time?
Sorry, I don't understand.
How do the secondary synchrotron photons have enough energy in the proton rest frame to pair produce?
You mean the photons which?
You want the loop, right?
Yes, but you produce a synchrotron photon. It goes, assume it goes and pair produces. Now the new electron is going to meet new photons. And these photons will have the same energy as the one before. Or if you are above threshold, of course the electron cools. But it can emit several photons which are above threshold for pair production.
Do you want inverse Compton with the same external photons? Or do you want synchrotron?
Yes, but you can do. But you can do the same. You can do the same loop with inverse. I don't think I will go very far.
Yes. Short talk will transfer very long.
We will continue tomorrow, don't worry.
And we have boat trip. We can discuss this on the boat trip.
We have 2 weeks.
This is essential that there are no doubts in the minds of.
But I mean, if you just can give example, because people are doubting. So if you just give an example, what is the magnetic field that you will assume? That will,
Yes, I assume. For example,
okay, let's get. He will give an example so that to convince you. Guys, let's.
assume. Let's make it simple. Assume that you have a magnetic field of 4 times 10 to the 3 Gauss, a little bit higher than what. So my big parameter is.
In what frame do you want the electrons to
Wait a second, he will tell you.
Sorry?
In what frame do you want?
There is only one
In the
frame.
frame that I have a blob full of relativistic protons. Earth frame.
Okay, let's now compute the energy of the synchrotron photon.
Okay, the synchrotron photons
Has to be in some
will have
field, right?
B gamma squared.
What is gamma?
Okay? In MC squared.
10 to 6.
What is gamma?
Gamma is of the electrons.
Yeah, what is gamma?
The
People want to have some numbers, I guess.
They
will be convinced
what is
then.
gamma?
Gamma electrons
Take
is
gamma
the
to be
protons.
10,
Yes.
10 to the 5.
Okay,
10 to
put
the
that
4.
to 5 now.
10 to the 4. So this is 10 to the minus 10 times gamma is 10 to the 8.
So gamma is 10 to 4. Okay.
So in this example, this is 10 to the minus 2.
Okay.
mc
perfect.
squared. So it is an X-ray
X-rays, okay.
for this example. Now, this X-ray, 10 to the minus 2 times 10 to the minus 4, which is gamma p, is greater than, is
One.
equal to 100, which is greater than 2, that is the threshold.
Yeah.
Therefore, this thing shows that you are above threshold for
You
doing
can
this step.
No, no, here, that's one thing. If your Thomson depth is, let's say, 70, then it's good. It's going to,
I haven't talked
it's going to
for-
thermalize.
Yes, but I'll talk about it. Actually, what happens is when there are more things to be considered when we put other processes inside. But this is what we try to do. But as a basic idea, this thing, assume that you are in a region where you have these relativistic protons and you have electrons, which of course are the same number, but they have much lower energy. Then this thing could operate. This is what I'm talking about. But if what will happen next is, I'll tell you in a while. I hope.
Also, don't you run into the opposite problem of fine tuning of the photon's energy, because the cross section is energy dependent.
For what?
For proton per proton.
Yes,
So don't you need to have some
yes,
fine tuning?
that's why
Don't you need to have some
without
fine tuning of the
this-
photon energy?
Yes, this energy dependence. This energy dependence appears here. This is exactly the energy dependence you're talking about. So if you are very close to threshold, you need very, very, very high number of protons to start running. But again, so
Also, but the next point is that if you go very high above the threshold, then inelasticity becomes much, much smaller.
yes, I'll cut it.
Well, one question: in what frame, the frame of this outflow? Of,
No,
He's not talking about outflow.
I'm not talking
What
about
are you talking
outflows.
about outflows?
I'm talking about something static.
talking
Because
about
I wanted to
static
convey the first ideas, but I think I won't go much further.
If you only have one static frame, then in what frame do the protons
Only
have?
No, no, no.
Random motion of protons, what's the problem? It's
I'm
random
talk-
motion of protons.
Random motion now?
Because
Yes,
this is just a
I'm
cloud. What
talking
are you
in a
talking
frame that I am. The protons are moving randomly in this, but they don't have a bulk.
Ideal speech. Ideal speech. Just
about? Okay, let's continue. Otherwise, we'll never cut.
One proton, you don't care about it.
Just one problem.
But the
Not
basic
problem.
setup was not clear from the start. I think
Yeah.
that's the main problem.
Jump into conclusions.
So the point is the following. Is the German taking, like in a football game?
Have some red cards.
Yeah, yellow card.
So for Boris, what we did is we used Monte Carlo results from Ray Prothero to model the per production rate. In other words, when you have a photon meeting a proton, what is the distribution of electron positive pairs you produce? In other words, here in this numerical thing that we did, we don't have a delta function anymore, so we use full emissivities. And what happens is the following: we try to mimic the same situation, have relativistic protons, and you start increasing the number of protons inside the source. And originally you find that nothing happens, but once you go above some critical number, then you start these are the photons, and you see that this from one to the other it increases by 20%. So very, very quickly you become, the photons grow spontaneously. And this is we try to have a numerical and an analytical marginal stability curve, and they are one within the other by a factor of 2 or something, or even less. So in other words, our delta function approximation that we did analytically are in very good agreement where we do the full problem using the exact cross-sections, exact rates, emissivities, and what have you.
Apostolos, can you give like physical numbers of what will be the critical density?
Sorry?
Can you give physical numbers of what will be the critical density of the proton?
Yes, I'll come to that. So, assume that you have a region where you start putting, as I told you in the beginning, you start putting protons in there. And what happens is that then you start seeing, photons remain at a low level, there is protons do not radiate much to start with, but once they start to reach a critical level, then the photons make a burst and they cause the protons to go back to the stable regime. So therefore it is like a prey-predator thing, and here it's a toy thing, I continued injecting protons, and therefore you see that as the photons go away, the protons start appearing again. They go up to some critical level, and then they make the photons shoot back again, cool the protons, and so you have some kind of duty cycles in this picture. So these photons, I repeat, are not external photons, are not like we use in the Compton scattering, they come from somewhere else or whatever. These photons are produced from the electron-positron pairs through this loop. So therefore, it's energy in protons which is given through this loop to electrons and positrons, and therefore later to radiation. So the protons are taking part of the energy and transferring it to something else, into photons. And therefore that's why once the photons go away, because the protons have gone into a subcritical regime because of cooling, there is nothing to sustain them there. The photons fly away from your source, and then you're back to normal. Back to where you have low net number of protons and no photons at all. And therefore you start building again your protons, and you start doing the same trick over and over again. So for Jonathan, now it is the time for the relativistic flow. Assume that you have, actually to do this, you need high column densities in protons. Therefore, it's a nice idea, but I don't think that it can be applied somewhere. I mean...
but which column density? Can you say the number?
What is the Thomson optical depth you need?
Actually, as I remember...
Yes, please.
As I remember, the main parameter is column energy density of protons, and it sounds like, as I remember,
you remember
energy column density of protons.
Yes.
It's like something like 10 to 26 or 27 over gamma of Ergs per square centimeter over gamma of protons. It means that if you have gamma like 10 to 4, therefore it will be like 10 to 23 ergs per square centimeters.
That depends on why. If the photon in the restaurant of the proton is about at this threshold, then just the cross section. So it depends on the energy of the photon. Relative energy.
The energy of the photons is like 1 over. You mean background photon? Oh.
Yeah, I can transform to the restaurant of the proton. And then
Okay, now, probably
Okay,
Apostolos can.
maybe you can say something like this. Yes.
Probably Apostolos can answer
Yeah.
if you want, because I mean.
So the question is the following. All right, I'll go quickly now. Assume that you put this proton thing in the relativistic motion, in a shock, for example, and now you assume that you have, it's like a GRB shock, and it's moving inside the external shock is moving inside some density of the progenitor wind, for example. Then you have the same thing, but now once the photons, the signal photons are produced, they have a chance of being scattered upstream and returning to your shock. Then what happens is that you have the same loop, but now it's boosted by this gamma squared of your flow. As a result, you relax very much both the column density of your protons, so your Thomson optical depth is not huge anymore, and at the same time, the criterion, the feedback criterion becomes B, the magnetic field over B critical, times gamma to the 5 must be greater than 2 in MC squared units.
Don't you assume all the photons are reflected?
Sorry?
Don't you assume that all the photons are reflected within a dynamical time?
Yes.
Because you have a huge
Yes.
optical
Yeah, but I'll come to that. So,
It wants 100% of the photons to be
I take
reflected.
a very simple picture. I assume
Well,
a sock
one
moving in
included,
some external
right?
region, and
If you have
what?
10 on one dynamical time, the cumulative would be like
also I don't assume any particle acceleration. Not that I don't want, I just don't want to put it right now. I just have to. I want to have only the particles that have gamma equals of the gamma of the flow. I mean, so this view doesn't exclude particle acceleration. I repeat, but it's an extra extra set of free parameters. So I wanted to have it as clean as possible without particle acceleration. So one can solve the adiabatic standard GRPR flow equations. We all know about this. This is the mass energy that is swept, and this is gamma, assuming that gamma has a risk. I mean, I don't know how gamma goes to high energy, right? So I assume that I take it from the time it starts sweeping matter, so and starts decelerating. Therefore, originally gamma is constant, and then starts going down. And here I take it gamma to be, I don't know, 400 or something in this example. What happens is that you find some regions, depending on their initial parameters, that both the feedback and the marginal criteria apply. In other words, you can find regions where you are like this green and the red line, that both criteria apply. In this case, your flow, this solution that I showed you earlier, is not so innocent as it looks because it has run into this instability. What happens? I just wanted to show you that you have to solve now the equations, assuming now a radiation rate and here a radiation drag force, and I assume that you have the usual injection to the shock front by this rate, but I assume that all particles are injected with gamma equals to gamma capital. So in other words, it's like having a Maxwellian or a delta function in particles. So no particle acceleration, I repeat. Then you solve three time-dependent partial differential equations. One for protons, one for photons, one for electrons. I have used the hadronic channels, which are proton, photon, and photopion production, and these are the electronic channels, which people use, for example, in AGNs and everything. The point is that once you have assumed what is your injection rate, which basically I inject from the shock itself, I mean from the what is the shock accumulates, this thing has no free parameters. So this is a curse and a blessing. I just wanted to show you, I made a test with a very young student of mine with the standard GRB afterglow, where basically I took the leptonic processes and this is what the code gives. This is her analytical solution, and it has a very good match. So what I do is I'll solve this kinetic equation across the shock as it's moving, and it's calculate then the synchrotron, the SSE model. And this is what happens now to our flow. When they become unstable, the protons have to burn their excess energy, and this produces a photon burst, and at the same time, this excess energy, this schematic only, goes down because this hot mass has been burned here. And of course, gamma, because of the radiation drag, because still you have this wind of the progenitor in front of you is producing a drag force, slows your flow. The German's putting pressure, so...
Felix, maybe...
Put under counter pressure.
No, I'm sitting here and it was absolutely clear now that there is no way that we can do 4 talks today.
We can do
So there is a way, we end up then.
No, I'm already now proposing that we will, with Boris, all these electromagnetic channels that we wanted to discuss, we will move to some other day. because this is just, it's clearly, either we will figure out what he's doing or it will be just a waste of time. So I will just propose that we will continue with only 2 talks today. Yeah, and with Boris we'll do some other day. I mean, we have 3 weeks in the, or 2.5 weeks. So, what's your? Yeah. So I mean,
first of all, I don't want to be an obstacle to anyone.
No, but I think it's important that people understand that people will trust more what you are doing, and this it will be more interesting, right? Yeah,
Okay,
I think we can have some more time.
No. By definition, in your model, you could not see the photons because the photons have to be reflected back, so they cannot they cannot escape, right?
No. It's not all photons. It depends. It's a probability. It depends what is my column density upstream. Therefore, you find an optical depth, and a fraction of it is reflected back. Therefore, is most of the
energy stays
a huge
there.
fraction of the. I mean, my optical depth is 10 to the minus 4 or something. So this means that
You factor it into your loop, right? So you have tau times gamma squared.
Yes, exactly. So this small fraction goes into the loop. All the others escape.
And not only that, if you want it to be realistic, you must take into account the photon travel time.
Yes. We took all this. So what?
It can't be so sharp.
Yes, no, yeah, of course. So what I have done in this numerical code is to take all the history from the time I started the run. Therefore, the photons are moving always r over gamma squared in front of the blast wave. Therefore, I try to keep track of all the history. So therefore, it's like the GRB has its own history in front of it. All right. I mean, as it's moving with the and I hope I have done it correctly. I don't know. I mean, it's all the previous incidents, all the outbursts or whatever has happened earlier are in front, because they are kept in the code. So that's why it's
so
quite a long code to run.
What's the Thomson optical depth through the wind, let's say? At
Depends.
this point when you have this.
I'll show you this in a moment.
Each loop takes a dynamical time.
So this is now numerical results. What I assume is that here, for example, this run is only with electrons, and this is with electrons and protons. If I don't go to, this is the burst that is produced because of this instability. If I don't run the supercriticality, then all the radiation is electrons. I cannot make protons radiate. All right, I mean, they all radiate at a very low level, so electrons are by far the dominant thing in radiating. But once I hit supercriticality, photons, the protons lose their energy, and therefore I make this burst. And you see here, if I have a non-drag force, then gamma goes normally, but if I use the drag force, then I have an abrupt drop here, and then it continues normally after the episode is over. So, this is another example. Assume that you choose the condition that you satisfy the feedback condition criteria. In other words, big gamma 5 times to the gamma to the 5 is always greater than 2. But you don't satisfy the marginal stability. And now you start, you do this example. You start increasing the number density of your, or the wind density, as to say, because it's the wind that counts, by a factor of 2 every time. So slowly you go from the stable to the unstable regime. So if you have low external density, you have a marginal stability that is not satisfied, and you are in the linear regime. The radiation is due to electrons. But if you are in the high external density, then you get in the non-linear, and you have radiation due to protons through this loop I told you. Therefore, you see that you don't go anymore linearly. If it was linear, you would have, this would grow by a factor of 2 every time. But here you don't go linearly, because exactly the protons come into play and start losing their energy. So I did the following like as the protons become supercritical, the photons start growing exponentially. So you see a very sharp increase of your luminosity. However, because the photons grow so much in the system, this leads to an explosive proton pooling. In other words, there are so many photons around that protons have to lose their energy, and very fast. Therefore, as the protons lose their energy, they go to the subcritical regime, and the photons saturate, because there is nothing more to sustain them. So you have exactly the predator. You have an abrupt decrease in gamma because of the drag force, and you have continuous proton cooling, so you have a steep drop in proton luminosity. And when the protons have lost their energy, the system moves in a linear regime, and the light curve is driven by the injection radiation of electrons, only nothing more. So you go to the usual afterglow also. And the protons contribute to the inertia, but not to the radiation at this stage, at later times. Now, what is interesting also is the radiative spectrum. The spectral characteristics are the following. You have hot electrons, which are the primary in the beta hydrogen, and what you have produced secondarily. You have therefore synchrotron component with a peak at this energy, is big gamma squared times gamma. So it is, because gamma small is gamma capital, in my case, it's big gamma to the cube. The inverse quantum component is on the reflected photon targets, and they have a peak, which is basically Klein distance, so it goes to gamma squared. But there is a third component. Because in the SOP you have all the pairs that start, that have been produced and start cooling because of radiation. So you have a pair front, a SOP front that is full of cold pairs. Optical depth is not even, it is 10 to the minus 2 or something like that, it's not to 1. But the point is that you have now quantum scattering or bulk quantization of the upscatter reflected radiation on the cooled pairs, and this is EB, the bulk photons, have an energy of big gamma to the 4, that is the reflected photons times gamma, which is big gamma to the 5. This is the threshold condition you give over. So if you operates close to threshold, big gamma to the 5 is equal to 2, therefore E big is close to 1 MeV. Therefore, this thing, the bulk quantization of photons, are basically a blueprint of the electron rest mass. So this is what spectrum I get the peak. You have the synchrotron peak, you have the inverse quantum peak, and you have the bulk quantized peak. I can change gamma as long as I'm in the unstable regime. This and this will move. This will not move as long as I am close to the threshold. Therefore, the peak here will always stay irrespective of what my choice in gamma capital is. Yes?
What is the ratio of number density of pairs that you're producing?
Yes, it is.
To the protons?
Depends on how you produce, how strong is the outburst and how much energy is converted. But I would say that it's 10 to the minus 2, 10 to the minus 3.
10 to the minus 3. So
10 to the minus 1. But it's not 10, it's not 100. At least in the examples I have run. So the optical depth is less than unity, the Thomson optical depth.
So that's fine, but the produced number of pairs is about 1,000 times more than the number of protons that you
Sorry,
have.
the number?
The number of pairs that you produce is about 1,000 times more than the number of protons that there are.
Why?
What? No, I'm asking.
No.
Otherwise you will not lose all the
No, because the photons come from the synchrotron radiation.
That's
So
fine. But I'm asking how many, if you look at the results of the calculations.
basically, all you can work on a limited number by saying that, okay, I have saturation, and what happens if I have saturation? I take all the energy that I have put in protons and turn it to electron-positron pairs, which later they cool. So therefore, this is the limiting number that you can get from this. You cannot go more than that.
So that's
2,000. Therefore, I guess I told you that these are not cases that go to saturation. I mean, you don't lose, protons do not lose all the energy, but I would say that still you produce much more photons than electron-positron pairs. Because each proton, each electron-positron pair produces many more photons because of synchrotron radiation. Synchrotron radiation, each electron produces lots of radiation because of...
That's fine. Do you consider per annihilation?
Per annihilation?
Yes.
Yes, but it's not important, because the optical depth is low. It's what the people were doing back in the 90s, but the optical depth must be much higher than 1 to start having strong annihilation.
Unless your multiplicity is more than 1 over the original optical depth, it's nothing.
Anyway, so this is the evolution, because I have this kinetic equations, I can get snapshots.
Cross-section should be the same or higher.
The multivariate.
Cross-section for annihilation should be higher than
how the
cross-section
spectrum looks at 1, 3, 10, etc. seconds. And you see this, I mean, this is the synchrotron, this is the inverse quantum peak, and this is the bulk component peak that is moving to lower energies, because both B, I have taken here B to drop like 1 over R, I forgot to tell you that, and gamma, of course, decrease. Therefore, the radiation after all this thing has happened, it goes to, becomes softer. These are the light curves that you get in various bands that correspond to the previous burst I showed you. So this is how you have the evolution of the bulk of the ice. You start at MeV, but later you move to lower energies. This is irrespective of what the other directly produced components are doing. So the question is, what is the optical thickness? How much mass you need to start all of this? And I have worked only for winds. I don't know what happens in uniform densities, but here it shows you for gamma. I mean, as you increase gamma, you go, because it's big gamma to the 5, and the Martian stability also depends on gamma, on the bulk flow. You need lower and lower energies to start to worry. So therefore, densities, sorry. So this means that if I am going to increase gamma, I go to lower external densities. And if I, of course, gamma is small, then I have to go to quite high ones. Therefore, this shows the total energy that is released as a function of what is the external density.
Apostle, if you translate this into mass ejection from a Wolf-Rayet
I don't know. I think this is 10 to the minus 5, isn't it? 3 times 10 to the minus 5.
Okay, so this corresponds to
yeah,
typical. Okay.
Yeah, this is the Wolf-Rayet standard.
Ejections you need for.
So, the conclusions are that the relativistic philosophy can become supercritical for external densities that correspond to Wolf-Rayet type stars. And magnetic, I have not used too high magnetic fields. I mean, something like an equipartition or a usual magnetic field that people use that drops like 1 over R or whatever, or even in equipartition is, I mean, I don't need a pulsar magnetic field to do this thing. So the part of the store of the proton energy is transferred into radiation, you produce a photon burst. Because of the supercriticality criterion, you see always a peak at 1 MeV. You have a fast initial cooling of protons, which produces a steep drop in the photon-like curve, and then a softening of the spectrum. And so the model predicts that the burst should be accompanied by soft emission, which is a synchrotron peak, hard gamma ray emission, which is the inverse content, as well as neutron and photopion from photopion production. So I don't think I have anything else.
No.
Okay, we will thank the speaker.
Just a question related, I might have missed it. The supercritical criterion.
Sorry?
The supercritical criterion basically says that the photons should have the electron energy, right? So that should be about MeV in the co-moving frame. So if everything moves toward us with Lorentz factor gamma.
No. This is in our frame, because the reflected photons in the frame of the co-moving frame is big gamma to the 4th. Now this is in the Thomson regime. Therefore, it is isotropic scattering in the frame of the co-moving frame. Therefore, when I boost it to my frame, it is gamma times big gamma to the 4th, so it becomes big gamma to the 5, which is my criterion.
If I can have a question.
Yes,
the chairman
he's
gave
trying
me
to ask a question from earlier.
So if you, when you say that you have Lorentz factor of the proton, let's say in the co-moving frame of the jet because of the shock,
yes,
the shock, like few hundreds, right?
Yes.
At the same time, if one believes what Anatoly is doing, Spitkovsky simulations of the shocks, that you would expect that electron will be almost in equipartition with the protons. You will expect that the electrons will be relativistic there, very much relativistic. Then I would say that I would expect that they will produce your supercritical conditions for electromagnetic cascades much before you have reached your conditions for proton cascades, because the optical depth, I mean, it's much more efficient process.
Could be. I agree. I mean, here I told you, I mean, I like to put, I mean, people, I mean, when we talk science, to have very well put our hypotheses, our assumptions. So my assumption is that both electrons and protons are picked by the process. Therefore, gamma mp c squared goes to, I mean, it's the energy of the proton. Gamma me c squared is the energy that goes to electron. Therefore, the ratio is mp over me. Therefore, most of the energy goes to protons. If I am to use what Anatoly is doing, then I have to increase this number, which I haven't done. I don't know what happens. Also, I have to put acceleration. I don't know what happens if you put a power law tail, because maybe you become unstable in at lower critical densities, because now you have protons that go to much higher energies if you put a power law tail. I don't know. I mean, I told you that all this wanted to show that what happens if you have as few parameters as possible. So